Okay. All right. Folks, does everyone have this? Yes? Everyone has this out? Do we have something to write with? Some people, you might want to use a highlighter, maybe some different colors. I don't know. If that's your style. I'm totally for it. Folks, so far in our coordinate geometry toolkit of formulas, we have the midpoint formula, yes? And that is one fantastic formula, which at this point doesn't have a ton of use. We're like, why are we getting the middle point, right? Why do we want that? Well, for right now, it seems we're just finding the middle of a line segment and then we win. But later on, we're going to be using that midpoint to do some pretty exciting stuff. So right now, what we're trying to do in these first couple of lessons in this unit is give you the tools, and then eventually we're going to run into some problems that we're going to be able to, for sure, figure out using these tools. Okay? So, coordinate geometry. First of all, let's recall here a point, or maybe a coordinate, yeah? It's a location in space, okay, in two-dimensional space. We should maybe talk about that. For grade 9, 10, and 11, we talked about two-dimensional space on an XY plane, yeah? Grade 12, you go into 3D space, which is what we live in as humans. Okay? So, points are just coordinates, X and Y. Yes, we're really familiar with those. Now, a line segment, it's not a line. A line segment, it's basically just a piece of a line. And it says here, there's a collection of infinite points between the two endpoints. And theoretically, there is, right? If we have endpoint A, and then we have endpoint B, there are an infinite number of points on this line segment. And not necessarily the craziest thing to like wrap your head around. Like, sure, if this coordinate was like 1, 1, then up here it could be like the littlest bit over, it could be 1.1, 1.1, or 1.011. And that's what they mean when they say an infinite number of points. And also, now that we have a line segment, don't forget about this, okay? Remember this? We spent the first week, reviewing grade 9 stuff, and slope. Slope will come into play, maybe not a ton today, but it certainly will come into play later on. Now, the slope of the line segment is the ratio of the vertical change between two endpoints, and their horizontal change. So, sounds a little weird, but what they're saying is it's just rise over run, yeah? Vertical change divided by horizontal change, right? So, rise over run. Or this was something that we haven't seen before, right? The triangles, delta y. Delta y, all that really means is the change in y. That's all that means, the change in y. Divided by delta x, the change in x. So when we're talking about the change in these values, it's kind of like on a table of values. It's really nice, right? You just go down and see the first differences. And that would be the change in y, or the change in x, depending on what side you're looking at. But really, what this is, and this one might be a little bit more familiar, is that the change in y is y2 minus y1. Remember that? That is the change in y. That's how y differs from one point to the next. That's the change in y. And we divide that by the change in x. And it's kind of wild. Like rise, delta y, the change in y, and y2 minus y1 all literally mean the exact same thing. They all do. Same with the run and delta x and change in x and x2 minus x1. They are all meaning the exact same thing. Any questions about that? Slope, change in y, change in x? You feel okay with that? Okay. Now, recall. Collinear points are points that lie on the same line. So for example, A, the midpoint here, and B, they're all collinear points because they're all in the same line. That came up maybe for 2 homework questions in grade 9, maybe 2. Area of a rectangle is length times width. Yeah, remember that? It's been a long time. I know, seriously. Or some people might say base times height, and I say, okay, sure, but length times width. Area of a rectangle is half the base times the height. You might read it like that, or you might read it like that. Yeah, however you like to do it, totally up to you. And these are great formulas that I think we're quite familiar with in grade 10. An equilateral triangle is a triangle with all the sides of equal length, and that's like, remember that? Types of triangles, there's 3 types, 4 types, 5, there's a lot of types. There's an isosceles triangle. It's when 2 sides are of equal length. Yeah, remember that? Good. A scalene triangle is a triangle with no sides of equal length. How about types of triangles? Can I get a thumbs up or a thumb to the side or a thumbs down? Okay. And lastly, the Pythagorean theorem. C squared equals A squared plus B squared. We love this thing. Where C, and I actually write it in here just to make sure, where C is the length of the hypotenuse. Because sometimes that's where, I remember when I was teaching this in grade 9, sometimes that's where the issues were, but we know that now in grade 10. Ton of information here, but it's kind of like a, oh yeah, I remember this. Now, to calculate the length of a line, we literally just use Pythagorean's theorem. Now, Pythagorean's theorem is really useful when you can see the coordinates on the graph. So for this first example, we can see the coordinates on the graph. Sometimes we're going to run into problems where we're not going to be able to graph because, 1, the coordinates are nasty decimals or fractions, or 2, the coordinates are just really, really, really unreasonable to graph. So what we're going to have to do, once we get comfortable seeing the points here, is we're going to develop a formula, similar to how we did it with the midpoint formula. We're going to develop a formula that we can calculate the length of a line segment between any 2 endpoints. Okay? So again, all it is really just Pythagorean's theorem. And we know Pythagorean's theorem, and you showed me that you know that. And we just got to remember, it says here, we will use line segment that connects the points A and B. So let's just say this is point A, okay? And this coordinate is -3, +2. Yes? And then down here is B, call it B. And this is 1, -4. Is that right? Yeah. Does it come out okay on your... Did the photocopier just eat this one alive or what? Well, it looks pretty good. It says here to calculate the length of line segment AB. And yesterday, you might remember yesterday I planted that little seed. Remember with the midpoint? You rise and run and then rise and run? Yeah? Kind of the same idea. The first thing they want us to do here is to draw a right triangle. Now draw a right triangle ABC for which AB is the hypotenuse. So this is line segment AB. Now, your right triangle can look 2 different ways. I personally like to see it like this. I don't know why. That's just the way my brain works. Yeah? But some of you may not like that. You might be thinking this. And to be honest with you, it does not matter the way you draw this thing, as long as you have the right triangle. So, I just want to see it this way. Here is right triangle, and for whatever reason, we're going to call this point C. It doesn't really matter, but we do know that that's the 90. Yes? The right triangle is created by drawing vertical and horizontal lines. Okay? So, we got it. It says here, calculate the rise, or the change in y, or y2 minus y1. Because as we talked about on the other slide, it's all the same thing, really. All these things are talking about the same thing. The rise of delta y, y2 minus y1. That's what they're talking about. It's the exact same thing. So, what we could do is, because it's on a graph, it's so good. We can just count. 1, 2, 3, 4, 5, 6. This is 6 units, this side length here. Good? Now, hey, what if the points were a little unreasonable? How else could we get 6 if we couldn't graph it? Well, delta y, this triangle y, is this going to help us? Probably not a whole lot, but hey, y2 minus y1, that's pretty good. I think that's pretty good. So if this is x1 and y1, and this is x2 and y2, then we could say, okay, well, y2, which is -4, minus y1, which is 2, and I know it gives us an outcome of -6. It does. It says -6, which is a little weird, yeah? But I promise you that's not going to matter, and I'll show you why. So either way, this is 6 for the vertical change. Cool? Now for the horizontal change, 1, 2, 3, 4. 4 units. 4 units, that is the change in x, or the run, or delta x, or x2 minus x1. Whatever it is. It's 4 units. And again, if we wanted to use x2 minus x1, 1 minus -3, which sounds like it's going to be 2, but 1 minus -3 is actually +4. So far, so good? So it says now use the Pythagorean theorem to calculate this thing here. So I suppose, hey, what happened to my B? Isn't this point B? There you go. Now, when we're talking about line segments, like this line, the red line here would be line segment AB. Yeah? So let's go ahead. So we can say c squared equals a squared plus b squared. Lovely. Now, when we say c squared, what we're really talking about here is ab squared. Right? That's the line segment AB. And that equals a squared, let's call that AC, plus b squared, we can call that BC squared. So far, so good? Okay. And now all we're going to do, how do I punch this thing down a little bit? Ah, okay, this is good. AB squared we don't actually know. AC is really 6 units long, so we can say, okay, well, 6 squared plus BC is 4 units long, so 4 squared. AB squared equals 36 plus 16. I'm running out of room. Can I move this thing? No? Great. I need a calculator because I do not want to drop the ball this close to the finish line. 36 plus 16 is 52. So I'm going to continue this over here. AB squared equals 52. And Allie, what was the inverse operation of square? Lovely. We're going to square root this side, square root that side. A little square cancels with the square root, and we get side length AB equals square root of 52. 7.2? Yeah? Can anyone confirm? 7.2. And we'll probably just say units. Because it's a length, like I know it doesn't say meters or centimeters or feet or inches or anything like that, but because it's a length, we should say some sort of unit. So therefore, the length of the line segment AB is 7.2 units. Not too shabby. How do we feel about that? Does that feel all right? Pythagorean theorem? Okay. Good. Now that we have a pretty decent understanding of that, let's think about this theoretically, okay? And when I say theoretically, I mean, well, over here they gave us specific coordinates. They gave us A is -3, 2. B is 1, -4, yeah? So what if we had any coordinate meaning A, I don't know, x1, y1, or perhaps B, x2, y2. Like what if we had any old coordinates there? How would we kind of do this? You know, like I said, we're eventually going to run into problems where the coordinates are given as decimals or fractions, or they're just unreasonable to see on a graph. Now, whoops. we do know that we have to use the Pythagorean theorem, which is c squared equals a squared plus b squared, correct? And on a right triangle, we're pretty good at this. We're like, yeah, this side length AB is called C. That's side length C in the Pythagorean theorem. This side length here could be B. I don't know. I always use B for bottom. I don't know why. And then this side length here is going to be A in the Pythagorean theorem. Now, if we look before, it was so nice because we were just able to count this, right? We could just count 6. We're like 1, 2, 3, 4, 5, 6. And we're like, yeah, that's 6 units. And this one here, 1, 2, 3, 4, that's 4 units, undoubtedly. But if we don't have specific coordinates, and we just have theoretical coordinates, like x1, y1, x2, y2, how might we get the length of, well, AC? What can we do? Or even A or BC? Anyone have any ideas? No? Well, what we're looking for here is the vertical change, yeah? Because if the red line segment is the line segment we want, yeah? We draw in that right triangle, theoretically. And this right here is what we call, from B to C, the vertical change. And we know it's a vertical change because it's up and down, and also because it grabs the lowest part of the A up to the highest part of the B. So, vertical change. If we go back to slide number 1, what was vertical change? Vertical change. The change in y. Y is the vertical axis, right? So really, if we wanted to get this line segment here, this little a, we could say that this is going to be y2 minus y1. That's how we're going to get a. And also over here, for b, this is called the horizontal change. The way we get this is by doing x2 minus x1. Yeah? And we kind of have that written right over here. They say or this one, whichever is positive. It doesn't have to be positive because in the Pythagorean theorem, it doesn't matter. Because what's going to happen is we're going to take that value and square it. If you square a negative number, you still come out with a positive outcome. So even over here, AC, the little b. And this is exactly what we're doing. So if we try to use Pythagorean theorem here, AB is the hypotenuse, right? Let me pull out red. AB squared equals A squared, which is side length BC, right here, plus AC squared, which is side length B over here. Now, sure, BC is really the change in X, and AC is really the change in Y, which doesn't really help us a whole lot. So what we do is we sub in, instead of the change in X, we'll call it X2 minus X1, yeah? Y2 minus Y1. And then what we have here is this wonderful formula. We can just, what's happening is we square root this side, square root the other side, and off we go. AB square cancels with square root there, and we have this formula right here. AB equals the square root of x2 minus x1 squared plus y2 minus y1 squared, and it's all under the square root. So if we wanted to calculate the length of any line, we could just use this lovely but kind of ginormous formula. Okay. This is another formula to add maybe to that toolkit. We got midpoint, and now we got length of a line. So, it says here, example, the points L, M, and N are vertices of triangle LMN. First thing it wants us to do here is draw this on a grid. Okay, here's a grid. So let's draw this 3, 0. That's L. 3, 0. M is negative 2, positive 5. That's M. And N is negative 5, negative 1. And I think I'm going to pull out a ruler, or I can just use this thing here, and draw in the vertices, or draw in the lines best we can. So nice. Take a moment to draw that thing. So just looking ahead here, we draw triangle LMN on a grid. Awesome. It says calculate the length of each side length to 1 decimal place. Usually, folks, we always just do 1 decimal place. That's just like the easiest. And then part C, use the lengths of its sides to classify triangle LMN. And that kind of goes with that first page, remember? Could be equilateral, like all the side lengths are equal. Could be isosceles, 2 of the side lengths are equal. Or it could be scalene, where all 3 side lengths are not equal. So let's go ahead and start calculating these. So first we'll do, I don't know, we'll just do this maybe in alphabetical order. LM, MN, NL, yeah? So let's say length of LN. Okay? And what I like to do is I like to restate the points of L and M. So here's L, it's 3, 0. And M is negative 2, 5. I restate them. I'll show you why. So in our formula, it's going to be LM equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Is that right? Double check. Good, good, lovely. Now here's the reason why I like to restate the points. Because now I can go to the coordinates and say, okay, here's x1, y1, x2, y2, and off we go. Ln equals negative 2 minus, and I cross them out. I'll cross them out as I go, just so I know I don't reuse the same one. Negative 2 minus positive 3, close bracket squared, plus 5 minus 0 squared. Lm equals, we get negative 5 squared plus 5 squared, right? And that's, we're just using BEDMAS here. Inside the brackets, now next to the exponents, we got 25, positive 25 plus positive 25, and we get the square root of 50, which should be just above 7, I think, the square root of 50. 7.07, so we can say 7.1 units. Okay, so LM, maybe I can go right to the triangle here and say LM, this is 7.1 units. Okay. Next we can do length of MN. M is negative 2, 5, and N is negative 5, negative 1. And we know where we're heading with this. So x1, y1, x2, y2. Now, we should always start with writing the formula. I know it's a long one. I'm with you. x2 minus x1 squared plus y2 minus y1 squared. Next, let's fill in the blanks here. Negative 5 minus negative 2. Oh, negative 5 minus negative 2 squared. And that is something to be a little cautious of right there. I'm going to put a little highlight there. Negative 5 minus negative 2. And then y2 would be negative 1 minus 5. Close bracket squared. And off we go. Mn equals, right? I'm using the calculator because the integers and the double negatives, they're going to throw me off. And I don't want that to happen, especially this far into the question. Negative 5 minus negative 2 is negative 3. Negative 3 squared plus negative 6 squared. Negative 3 squared is positive 9. Negative 6 squared is positive 36. What's 9 plus 36 in the calculator is root 45, which should be maybe a little bit less than 7. Take the square root of 45, 6.70, so 6.7 units. Okay. I'm going to go to my drawing here. 6.7 units. So far, it's not looking like any type of triangle other than scalene. Unless this one is also 7.1, that'd be nice. Okay. NL. Length of NL. The coordinate for N is negative 5, negative 1, and L is 3, 0. Here comes the formula. x2 minus x1 squared plus y2 minus y1 squared. x1, y1, x2, y2. So x2 is 3 minus negative 5. Be very careful again here with that double negative going on. Plus y2 is 0 minus negative 1 squared. Notice that the square root symbol goes all the way across, right to the very end. That's important. I mean, it might not seem important in grade 10, but for sure, moving on in math, we want to keep that thing right across. And also, that counts for math form. So I'm going to double check this. 3 minus negative 5, 0 minus negative 1, squared. Okay. In the calculator, 3 minus negative 5, positive 8. 8 squared plus 1 squared, 64 plus 1, root 65. The square root of 65 is 8.06 or 8.1 units. So we go to the diagram. This is 8.1 units. Okay, last. Therefore, what type of triangle is this? It's a scalene triangle. This is a scalene triangle. And we should also justify it here. Because all side lengths are different lengths. Now, folks, using this type of formula for lines that we have on a graph, it hurt me as much as it hurt you. I promise. Does anyone have an alternative as to what we might be able to use if we didn't want to use it and we had a graph? Like, think about it. Let's look at LM. LM, yeah? LM, this right here. If we wanted the length of LM, which we know it's 7.1, we totally know that. We could draw in, using vertical and horizontal lines, a right triangle. See that? And right away, it's going to be super easy. Look at this. How long is this side here? Well, 1, 2, 3, 4, 5. This is 5 units long. Strange. Yeah? And how about this one? 1, 2, 3, 4, 5. Our rise over run inner selves in grade 9 might say, oh, you went down 5, so negative 5. But either way, it won't really matter. But hey, look. That's just the change in y and the change in x. So 5 squared plus 5 squared is 50. Square root 50, and that's our answer. Yeah? And that method can work if you have it on a graph. If you don't have it on a graph, because maybe the numbers are unreasonable, that's why we have the formula. The formula is great. Yeah? But is there a more efficient way? Absolutely. And that'll work for all of these side lengths, folks. Like, how about MN? If we look at MN, boom, boom. We draw in that right triangle using vertical and horizontal lines. The vertical change here is 1, 2, 3, 4, 5, 6. 6 units. Yeah? We're not shocked by that. And then the horizontal change, 1, 2, 3. 3 units. Okay? We're not shocked by that. I know in the formula we have here -6 and -3. And that happens because it kind of depends on which one's x1 and y1 and which one's x2 and y2. That'll change the positive or negative. But at the end of the day, it doesn't really matter because we're squaring a negative. We get a positive out. If that was +3 squared or -3 squared, we still get a +9. Yeah? Same with -6. We still get +36. And it's really just an exaggerated Pythagorean theorem that needs to be exaggerated because, well, if we can't graph it and can't actually see it, then we would not be able to use this idea here. Yeah? And lastly, over here, look, 1, 2, 3, 4, 5, 6, 7, 8. 8. You like that? And then 1. 1. So when I told you at the beginning here, this is really just the Pythagorean theorem. It is. It truly, truly is. It's just morphed in a way to work for coordinates as opposed to just side lengths. Yeah? Questions? Okay. There's some homework here, folks, on page 87, 1 to 5, 7, and 9. It's length of a line, length of a line, length of a line. The formula is great. If they give you a graph, there might be an easier way to do it. Yeah? So we now have 2 awesome formulas in our toolkit. We got midpoint and length of a line. Actually, remember the first question, I took linear algebra part 1 at university, and the first question was, how do you solve for the length of a line? Or actually, the professor said, how do you solve for the magnitude of a line? And I answered it, and that was it. That was the answer. Okay, cool story.
That's it for the YouTuber.